Okay, you have to be close because we have to look at this in quite intricate detail. So what we're looking at, if we fire a laser at the paper, there's a whole lot of stuff going on. And so what we can see is that the laser light is coming in along that line there. And we can see inside this block of glass here, look, it changes direction and it cuts across the glass like that, but then it comes out again at that angle there, and it comes out of the glass about there. So what we can see is that as the light enters the glass, it bends into the glass, and so to understand how this bending happens, we draw what we call a normal line, which is at right angles to the surface, and we can measure that angle between the normal line and the ray of light, and we call that the angle of incidence. As the light goes from a less dense medium to a more dense medium, it bends towards the normal, and then as it goes from the more optically dense medium back out into the air, the less optically dense medium, it bends away from the normal. So we say that the glass, has a high refractive index compared to the air that's got a lower refractive index. So optical density, refractive index are synonymous to each other. You can also see there's a whole lot of reflections happening. Like you can see our angle, our incident light is reflecting off and some's going there, and also some of the incident light is reflecting off that boundary there and going out there. What we're interested in is just the light that's refracted, just the light that goes into the glass and then out of the glass again.
So was my filming good?
I haven't looked at it yet.
I'm sure it was terrible.
Oh, I have. Yeah, it's fine. It's on. It's up. You're on Famous. You're YouTube.
You're on Famous?
You're an insider.
I am.
Okay. So kids.
Can you mute the bit where I zoom in?
Yeah.
Thanks.
So refraction, when we talk about refraction, it's the bending of light as it passes from one medium into a different medium. We talk about those different media having different optical densities. And so air, medium 1, we say it's got a refractive index of, it's actually 1.003. These numbers are all relative to a vacuum, so we kind of found these numbers, these optical densities, these refractive indices, by looking at how much light bends as it passes from a vacuum into another material. And it turns out that light does bend just a tiny little bit as it passes from the vacuum of space into the atmosphere of the Earth. And so air has a refractive index just slightly fractionally higher than 1. Light bends quite a lot as it passes from a vacuum into glass. It bends enough to generate a refractive index of 1.5. So glass is much more optically dense than air. It's got a higher refractive index than air. These refractive indices, these N values, they are just numbers. They don't have a unit. It's just a number because it's telling us how much the light bends as it passes from one medium to another. When we're measuring our angles, it's really important that we're not measuring our angle from the boundary between the air and the glass, but rather from the normal line. That normal line is the line that's always at 90 degrees to the boundary. And they'll often try and trip you up in an exam situation. They'll often give you this angle down here and leave you to make mistakes unless you realise that they haven't given you the correct angle. So always check that your angle is measured from the normal line. The angle of the light going in to the boundary is called the angle of incidence. So we write theta I. The angle of light coming out from the boundary, measured from the normal again, is the angle of refraction. We call it theta r. And a really typical classic question that you might get about refraction is we've got medium 1 of air, 1.00, medium 2 of glass, 1.5, angle of incidence of 60 degrees. How much is the angle of refraction? So, we've got Snell's law. N1 sine theta I equals N2 sine theta r. So that's the equation that we can use to solve all of our refraction problems. So what we have to get really good at is rearranging this, and in particular, how do we separate out the angle from the sine function? A sine function, it's not like another mathematical operator. We're not going sine times by the angle, right? The function is something that works on the angle and pops out a number. So let's have a crack at using this equation, work it through together to solve this problem. In this case here, we're trying to separate out the theta r, so we have to rearrange this equation to make it theta r equal. So we're going to move everything away from the theta r. Starting with N2. How's N2 connected there?
You're timesing it.
Times. So what are we going to do?
Divide.
Divide both sides. This is the piece where we can make mistakes. How do we get rid of the sign?
Divide.
That's the mistake that we can make. How do we get rid of this? What we have to do is inverse the sine function. So that means on both sides, so here we went divided by N2, divided by N2, sticking to that thing of as long as we do the same thing on both sides of the equal sign, our equation is still true. What we're going to do is take the anti-sign, the inverse sign of both sides of the equation. So we're going to do sine inverse of that is sine inverse of all of that. So the next line of working is going to look like. So now we've managed to write it in terms of theta r. We're going to plug some numbers in. And so we plug some numbers into that.
I've got 35.26.
That sounded right.
Okay, that
because it was
time I
small.
got 35.26.